to the second part of advanced theories of covalent bonding. And in this portion, we're going to talk about the molecular orbital theory. And the reason we need to move from valence bond theory to molecular orbital theory is because there are some properties that we just can't predict using the valence bond theory. So we're going to move to this molecular orbital theory. And by the way, I have abandoned for the time being trying to have my picture on here because I can't quite figure it out yet, but I'll keep working on it. So molecular orbital theory, what is it that we're trying to accomplish? Well, um, if you think about a theory is supposed to be able to predict the way in which things behave. And we're trying to predict the way in which molecules are behaving, right? And so it should make sense that we need to go to a more advanced theory that considers the molecular orbital instead of these atomic orbitals that have some kind of hybridization. So as we move along here, one of the most significant properties uh, that we do not have the ability to predict in valence bond theory is magnetic character. Okay, and so oxygen molecules, oxygen actually, these oxygen molecules actually are magnetic, right? They have a magnetic quality to them, and so they are held within a magnetic field. On the other hand, um, nitrogen molecules, right, do not. So why is that, and how can we use molecular orbital theory to one of the ways that you're going to see that we can go ahead and predict this is using something called a GUI balance. And this GUI balance um, allows you to put a sample in a magnetic field and to then look at the attraction. Okay, so in this balance, um, you've got the sample uh, inside this test tube device. You've got that hanging on a balance, and then you have some sort of counterweight on the other side that allows you to determine exactly how much force is being applied. So this is just a picture of a way that you could do it. Most of them are electric in nature now. So there are these four really important things to remember as we work through molecular orbital theory. So the first thing is that the total number of molecular orbitals has to be equal to the total number of atomic orbitals that are contributed by the bonding atoms. All right, so an atom is only going to contribute its valence orbitals. Okay, keep that in mind. We're only going to work with valence orbitals. So we haven't really changed that, and all of bonding, we focus only on valence orbitals. There are going to be two types of molecular orbitals formed. One is a bonding orbital, and one is an antibonding orbital. The bonding orbital is going to be a lower energy orbital, and the antibonding is going to be a higher energy orbital. The electrons, in much the same way as we fill electrons um, in the atomic orbitals, are filled in order of increasing energy. Okay, so we're going to go from lowest energy to highest energy, and we're going to pair them up only when we absolutely have to. So atomic orbitals combine and they're going to produce molecular orbitals, and it's most effective when those atomic orbitals are of similar energy. So if you think about that, you think about the valence levels in the same row, right? And so those are going to be the most effective. Not that they won't bond in others, but the most effective are going to be in the same. So if you think about the ways in which things combine, think about waves, right? We talked before about wave-particle duality in Gen Chem 1. And in wave-particle duality, waves can combine in two different ways. There can be this constructive interference, and there can be destructive interference, right? And so the constructive interference results in a wave that is more intense. Think about lasers, right? And how we actually um, get that signal stronger and stronger and stronger, and it's through this constructive interference. But then there's the opposite of that, and that's the destructive interference, and that's when these are completely out of phase. So when these are completely out of phase, they cancel each other out, and the wave is gone. Okay. So think about atomic orbitals, and if you were going to combine two s atomic orbitals, like you might do in the H2 molecule, those two s orbitals would combine to create an antibonding orbital and a bonding orbital. Right? And now we're introducing something that we've seen before, and that's sigma. Okay, and sigma is used to indicate single bonding systems. Okay, so when do these things combine, and how are they most effective? Well, they combine very well when you have an overlap. And so if you put these two together, these are p orbitals, right? And these two, when the lobes are not, right, of the same um, energy, then you get the antibond, right? So in this case, we've got bonding, and in this case, we've got antibond, right? So we've taken two atomic orbitals, p orbitals. This says we use the px, right? And if you look back on the slide before, it was a sigma s because we were combining s's. Now the specific p's can be designated, and we can talk about combining px, py, and pz. Okay, and in this case, we're looking at a different combination. And in this combination, what we have is an antibonding, what we call pi orbital. Right? So now this is pi is when we talk about double bonding. So you notice over here, right? These p orbitals are aligned parallel to one another, right? And so you get the overlap, right, on both ends of the lobe, right? And that is not the direct overlap that we looked at with the sigma. So the pi overlap is a little bit different, and that we'll talk about along here. So you can have px direct overlap. You can have this px. Can you have then this py overlap? Well, these are not oriented properly. And what about this py, um, pi type of overlap, right? So if we were to ask this question, hopefully you're looking at this and saying, well, this is really the best, right? Because you have the direct overlap, right? And the orbitals are of the orbital ends are of the same sign, okay? So they're in phase, and that combination would result in a molecular orbital. It would result in a sigma px. Okay, so let's look at the ways in which we combine these things. And the ways in which we combine these is called linear combination of atomic orbitals, or the LCAO method. Right? So the LCAO method says, let's take the easiest molecule. Let's take the H2 molecule. We take the S from one of those H's and the S from the other H, and we combine to form something that is a sigma 1s, a bonding sigma 1s, and then we also have to get a anti-bonding or a sigma star 1s. And then if you remember these from back in Gen Chem 1 where we were doing atomic orbitals, the Pauli exclusion principle and Hund's rule, well, those electrons from each of the H's are now thrown into the pot, basically. Okay, they're thrown into the pot of the molecular orbital, and you fill them in the lowest possible energy. Before you move up in energy, right, before you move to the higher energy, you have to pair them, right, because they're going to be, it's the same principle here that you have two electrons in any one molecular orbital. Okay, so you fill that thing up. Here is the 2s 2p combination. Now this gets a little bit more complex, but it's really not that bad, okay? Think about it. We take 2s of each, so now we're talking about beryllium, and we take the 2s from one beryllium and the 2s from another beryllium, and we create the sigma 2s and the sigma star 2s. But beryllium also has two p's. And so now when we combine these two p's, we get one sigma 2p and we get one sigma star 2p. Right? And that comes from the 2px. And then the other two are pi. Okay, the other two combinations are pi orbitals. Okay, so here's the 2py and the 2pz. And then they also have they also have antibonding orbitals, the 2py and the 2pz sig or pi stars. Okay, so those antibonding orbitals are now actually of lower energy than the sigma star antibonding orbital, and that comes into play in several of these instances where we're trying to predict the properties. Okay, if we look at the second period, right, if we look at the 2s2p, these are all of the molecular orbitals, right? So these have all been combined. And we can start off from the bottom. We know that the bottom one is going to be the sigma 2s. We know the next one's going to be the sigma star 2s. And then we can start to look at this sigma 2p, right? And we can kind of look at the energy differences in this sigma 2p, right? The energy differences in this sigma 2p, it goes up, right? And that sigma 2p actually goes higher than the pi um, 2p's, right? So the pi 2p's remain relatively flat. You can see this going across. It's relatively flat in terms of its energy. And so there's this inversion, if you will, right? When you get to the N2. And that says that, wait a minute, now I got to fill this one. I'm going to change color here real quick. I got to fill this. I got to then fill this. And then I got to fill these. Right? And finally, I fill the the last of the bonding orbitals, right? And then I go up into the antibondings, right? And the antibondings have a similar upward trend, but they don't switch places, right? The sigma star and the pi stars stay in their normal, right? In their normal state here of the pi's being a lower energy than the sigma, right? The sigma stars. Okay, so there's no what we call mixing in the O2, F2, or Ne2. There's none of the none of this mixing of the sigma 2p and the pi 2p's, right? Where the pi 2p is actually a lower energy than the sigma 2p as we move through N2 all the way back to Li2. Okay, so when we look at this without mixing, right, standard, the sigma, sigma star 2s, then you got the sigma 2p, pi 2p's, pi star 2p's, sigma star 2x, or sigma star p. Here with the mixing now, it goes sigma s, sigma star s, and then the pi, right, is the lower energy. So the pi 2p's are in lower energy than the sigma 2p, which is right up there. And then you go up to the sigma star 2p's and then on up to the, I'm sorry, to the pi star 2p's and then on up to sigma star 2p's. So that mix, especially when we start talking about how the how we predict. So one of the things that I started off with was that oxygen is what we call paramagnetic. It has magnetism, and in having magnetism, it actually responds to that gooey bounce. Why does it have magnetism? Well, it's right here. It's in the fact that the pi star 2p's are only half filled. And so when you have half filled um, molecular orbitals, uh, you have magnetism. Okay. Okay. So let's kind of wrap some of this stuff up. Um, when you talk about the valence bond theory, right? Um, you're only talking about bonds localized between two atoms, right? And you do this overlap stuff, and you know this sp, sp2, sp3, um, sp sp3d, all of that stuff allows you to predict shapes, right? And then you can also predict the sigma and the pi bonds. That's great, right? But it's only on where the electron density is, and you have to be able to look at a bunch of different structures if we talk about resonance. But if we move on to this higher level, this molecular orbital theory, it talks about delocalized electrons, right? It's the molecule, right? That should make some sense to you guys. It's the molecule, and then it combines these atomic orbitals to look at molecular orbitals that are defined as the sigma star, the pi, and the pi star orbitals. Right? That means that we then have bonding and antibonding interactions, and we can then predict whether or not something will bond by looking at that. Right? And then again, it predicts the arrangement of electrons in molecules. All right. So that's all we've got for chapter 8. We'll move on to our next chapter, and I'll put that one up soon. All right. Thanks for listening.